Welcome back to Integral Calculus. In this video, I want to introduce you to integration by parts, perhaps one of the most powerful techniques of integration that we have at our disposal. Integration by parts is really just the product rule for differentiation reversed on itself. Let me get my head out of the way, and I'll show you what I mean. We know that if we have two functions, u and v, both implicitly functions of x, and we try to differentiate with respect to x, we're going to get the derivative of u times v plus u times the derivative of v. If I, from here, choose to integrate both sides of this equation, well, then I'll have the integral of the derivative of u and v with respect to x equals the integral of u prime times v dx plus the integral of u times v prime dx. On the left-hand side, the fundamental theorem of calculus tells us that when we try to integrate a derivative, they're going to basically cancel each other out, and we'll just be left with u times v. On the right-hand side, I can do a u substitution. Literally in this case, because I'm going to think about u of x. Well, then du would be u prime times dx, and that first integral is v du. In the second integral, it will be, I guess, a v substitution. If I think about v of x, then dv would be v prime dx, which is right there, and I have u dv. From here, just rearranging a little bit, and the typical way of writing the formula for integration by parts is u dv equals uv minus the integral of v du. Now, when you are looking at an integral, for example, the integral of x times sine of x dx, I immediately, when I'm looking at this integral, recognize that I've got two functions being multiplied together. I need to choose one of those functions to be u, and then the other one, and whatever else is left, will be dv. How to choose which one, I'm going to talk about in quite a bit of detail later on in this video. But for right now, I ask you to just accept that we're going to let u equal x, and then dv will be the rest of it. Sine x dx. Once I have made that decision, I look at what I need. I need u, v, and du. I have u. I don't have du. In this case, that's going to be pretty easy. If u is equal to x, then du is equal to dx. Having u, finding du, that's something we've done for integration by substitution since before the start of this course. dv is a little bit more challenging because we have to go backwards. If dv is sine of x dx, then v is going to be the integral of sine x dx. I guess I should write this out. It's the integral dv, just integrating both sides of this equation. But the integral dv is just v. And then the integral of sine is the negative of cosine of x. And technically there should be a plus c here, but for integration by parts, it turns out that we actually need an antiderivative, not the indefinite integral here. So we choose the value of c that is most convenient for us, which is almost always c equals 0. Later on, we will need a constant of integration. We just don't need it yet. Right. So all of that is our integration by parts side notes. Usually we don't bother writing out this line. If you want to, there's nothing wrong with it. But just for the sake of tidiness, I guess, we don't write it out. But then we use the integration by parts formula, which doesn't quite fit on the screen with all of the derivation we've just done. But I know what it is, and you have it written down in your notes. We need u, which is x, times v, which is minus cosine of x, minus the integral of v, which is minus cosine x. That minus can come out and turn this into a plus, times du, which is just dx. So just cleaning up that first term, that's just minus x cosine x. Nothing too exciting there. The integral of cosine of x is sine of x. And here at the end, we do need to insert our constant of integration. If you work through and differentiate this, you will find that you get x times sine of x minus cosine x plus cosine x, and the minus and plus cosine cancel each other out, leaving you with the x sine of x that we claimed, or that we started with in the original integral. All right. So there's the basic idea. And I guess now all that's left is to figure out, how do you determine what is u and what is v? The answer to that is both simple and complicated at the same time. I probably should have left this on the screen, because talking about some of this stuff in blue, I think, is where the interest is going to come in. Whatever we choose as u, we're going to differentiate. Whatever we choose as dv, we're going to integrate. And that's really our clue. We want to think about our functions and think about what makes a function easier or harder to work with when we differentiate or when we integrate. And so I want to remind you of the various functions that we have looked at. In no particular order: inverse trig, logarithms, polynomials, rationals, radicals, trigonometry, and exponentials. That pretty well encompasses every function that we have studied in calculus up to this point. And okay, I lied. This is, in fact, in a particular order. Starting at the top, if you take the derivative of inverse trig, you end up with a rational. Rationals are definitely easier to deal with than inverse trig. If you integrate inverse trig, well, I have no idea. So we definitely want to differentiate inverse trig, no questions about it. Logarithms, kind of the same thing. If you differentiate a logarithm, you end up with a rational. If you integrate a logarithm, I don't know, we actually haven't done that yet. So those two are on the definitely differentiate pile. Polynomials are kind of an interesting case because whenever you differentiate or integrate a polynomial, you're going to end up with another polynomial. When you take the derivative, it's going to be a polynomial of a smaller degree, which is definitely better. But when you integrate, you're going to end up with a polynomial of larger degree, which isn't the worst thing that can happen. So with polynomials, we're going to put that on the probably differentiate pile. Rationals and radicals, I think, kind of fall under the same sort of category. For rationals or radicals, well, differentiating is going to make things worse, but we may not be able to integrate. So, I mean, we're going to hope that we can differentiate. And if that's not what works out, well, then we're going to hope that we can actually do the integral. Although, honestly, when it comes to rationals and radicals, very often the answer is that this is the wrong method to try to work with those things. Trigonometry, well, sines and cosines are easy. The derivative of sine is cosine. The integral of sine is negative cosine. Either way. The uglier trig functions, well, the derivative of tangent is secant squared, which is definitely worse. The integral of tangent is the log of secant, which I don't even know if that's better or worse. So either way, we're just going to hope that things work out okay. Exponentials are our favorites, right? The derivative of e to the x is e to the x. The integral of e to the x is e to the x. So the answer here is either way. What I do notice in this process is that none of these came up and I said, yes, integrating this is lovely. Differentiating it is annoying. That's just not a thing. So we have a list from definitely differentiate to usually differentiate to hopefully differentiate to I don't really care. And if you remember that it's true, lazy people ride the elevator, it's not that difficult to remember this order of these functions. Right? It's true, inverse trig. L, logarithms. P, polynomials. R, rationals and radicals. T, trigonometry. E, exponentials. In this order, pick U. And then the rest is dV. If I scroll back up to that earlier example, I had a polynomial and trig. I chose the polynomial to be U, and then that left the rest of it, the trigonometry, to be dV. So that's how we can make those sorts of decisions. How about something a little bit harder? This function looks very similar to the one we just finished, x times the natural log of x. It's an x multiplied by a transcendental function. Although this time our transcendental function is a logarithm, and we know that logarithms are very well behaved with differentiation and not so well behaved with integration. So maybe we should let u equal the natural log of x. That would leave dv as everything that's left, x dx in this case. Once we have that, du is going to be 1 over x dx, and v is going to be 1/2 squared. Integration by parts formula, it's going to be u times v minus the integral of v times du. And as ugly as that looks, it's really not that bad. We've got 1/2 x squared times the natural log of x minus 1/2 the integral of x dx. The integral of x is just 1/2 x squared. Multiply that by the 1/2 in front. And add our constant of integration. I'm going to look at one more example. The integral of x squared times e to the x dx. This one is notable. It follows the same pattern as the first one we did. We've got a polynomial and we've got an exponential. It's definitely going to be in our best interest to let the polynomial be u, and then the exponential will fill in our dv. Because by doing that, we end up with a simpler polynomial as du, and well, the integral of e to the x is just e to the x. There's not a lot going on there. That definitely makes our lives easier. So we've got u times v, that's x squared e to the x, minus the integral of v e to the x times du, 2x dx. And wait a second, this isn't as nice as the ones we've been working on. I don't know how to integrate 2x e to the x dx. Yes, I do. We just talked about that. We integrate that by using integration by parts. That's right. Integration by parts is so nice and so much fun that sometimes you have to stop in the middle of integrating by parts in order to integrate by parts again. All right. So our x squared e to the x out front stays out front. We do have to be careful with this minus and make sure it gets distributed. So it's minus u times v, 2x e to the x, and then minus a minus will be plus the integral of v du. Finally, at this point, that's an integral I know how to do. And there we have it. As far as I'm concerned, that's the best way to write out this result. Although I do want to mention that I have seen more than one textbook who at this point would say, oh, we can factor out the e to the x, and that makes things nicer because now it is clearly a polynomial times an exponential. I think it's worse, but what do I know? All right. So that's the basic idea of integration by parts. Let's wrap up with one for you to try. Not sine, cosine. So I would like you to take a look at the integral of x times cosine of 3x dx. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.